Okay, good morning, everyone. My name is Zhenyu Zhang. I'm the postdoc researcher in ReconIP. So today I'm the chair of this seminar. Today we will have Professor Pang Wei Kong to give a talk about the reliable data use. So firstly, I will give a brief introduction of Professor Pang Wei Kong. Pang Kong is an assistant professor in the Allen School of Computer Science and Engineering at the University of Washington, a visiting researcher at AI2 and a Singapore AI visiting professor. His research interests are in the theory and practice of building reliable machine learning systems. His research has been published in Nature and Cell and featured in medical outlets such as the New York Times and the Washington Post, and recognized by the MIT technical review innovators on the 75 Asia Award and the Best Paper Awards at TrustML and KDD. He received his PhD and BS in computer science from Stanford University. Prior to his PhD, he was the third employee and the director of the partners at Coursera. Okay, let's welcome to Professor Wang Wei Kong.
Thank you for the introduction, and hi everyone. Thanks so much for having me here. Super excited to talk to you all. Okay, so today I want to talk a little bit about data. And please feel free to interrupt at any point. There should be time for questions. Okay, so as I'm sure all of you know, a lot of the recent progress in AI has been driven by the scaling up our training data and scaling up the associated compute needed to process that training data. Okay, so this plot is from the recent Llama 3 paper, but you'll see many versions of this in other papers. Yeah. Okay. So yeah, so this plot is from the Llama 3 paper, but it's not special to it. And it's not, of course, just about text too.
Okay.
Oh, thanks. Okay. All right, great. Okay, so not just about text, right? So for images, there's the Lion dataset of web crawl image text pairs. Then there's also been an explosion of data and corresponding models in many other domains, like in histopathology, and recently released a new state-of-the-art model by sort of scaling up the amount of slides that they use to train it on, protein modeling, and so on. Okay, so I think this area is really just getting started, right? So there's been a lot of interest in open source, like training data sets and strategies for how to curate and filter these data. So last month, we released a Datacom LM. This is led by Ludwig and Vaishal, where we tried to figure out what kinds of curation strategies are most effective for language modeling pre-training. And at AI2, we are working on the open language model project, and we have open source data sets like DOMA that we release accompanying it. Okay, so tons of work here ahead of us in terms of further expanding and curating these data sets. Okay. But today I want to take the chance to look beyond these questions a bit. Okay, so today I want to take the chance to look a bit beyond our ongoing efforts in curation and filtering and talk about some slightly longer term questions on how can we better use our data to build more reliable models. Okay, so here's what we'll cover. First is, can we use this data, our existing training data, to generate even more training data for free, right? So through synthetic data, and when and why might we hope that that works? Second, instead of just scaling up our training data, can we scale up the data that our models have available at inference time instead? And third, most of our training data is static. So it's collected from things like news and books and Wikipedia. So what happens when we deploy our models in more interactive settings? Okay, feel free to stop me anytime for questions. If someone is could you help to look at the Zoom questions as if there's anyone, please feel free to check. Thank you. Okay, great. So let's dive in and start with training on synthetic data. This is work led by my student Scott. Okay. So the question we are interested in is, can we use synthetic data to improve the best models that we currently have? Okay, so this is different from using synthetic data to distill GPT-4 or some other stronger model. Okay, can we use a model to improve itself? And this is a really tantalizing question because if it works, then we can get data for free. We can have more control over the data. We can sort of target it however we want, and we can bootstrap and self-improve our models. And training on synthetic data does seem to work well in practice. So there's been work like self-instruct and so on, where this bootstrapping has actually led to big gains. Okay. Now, on the other hand, from an information theoretic perspective, right, it seems like there's a bit of a free lunch. Right? We have the data processing inequality. So how are we getting something out of synthetic data from the same model? So as a case study, we looked at the recent Sinclair paper. This is from Google MIT. And it's very cool work. So what they did was they first generated 150 million captions from Llama 2. And then they used these captions to generate 600 million images from Stable Diffusion. And then they tested it on a variety of downstream tasks. So here's the accuracy of the original clip model. So this is like the OpenAI clip model off the shelf. Each column is a different task, and the two rows are different model sizes. Okay. And this is the accuracy of their Sinclair synthetic clip model, where this purely trained on synthetic data. And if you zoom in on the aircraft task, which is a sort of fine-grained classification task where you're supposed to tell different types of aircraft apart, then you can see like very large gains here. The other gains are not, on the other task, it sort of matches the performance, but large gains on aircraft. Okay. So this is really interesting, right? What is driving these gains on the task? Now, our hypothesis is that synthetic data lets us control the training distribution and target it towards specific regions that are more relevant. So, and this, in Sinclair, they generated the synthetic data by first sampling class names from the downstream data sets in these proportions, okay, and then using those class names to generate captions, which then generate the images. Okay? So as you can see, 5% of the synthetic data, training data, was generated with aircraft labels, which is, in our estimate, about 10x more than what you get in a web crawl data set, in the real training data set that's used for training like the clip models, which is Lion 2B. Okay. So in this way, some of the synthetic training data is upsampling data that is relevant to the task we care about. Right? And this should be very familiar to all of you. Importance weighting and so on. Okay, cool.
So if you just weight the original objective with different weights.
I have the same question. This is unfair comparison because there are two factors. But one factor is that you increase the class probability. The other factor is you generate some synthetic data. You don't know if you don't generate synthetic data, you just use the original data because there are already many original data just because the class probability is very small.
Great. Thank you for asking that question. Maybe I don't even need to motivate this. Yeah, so exactly that is the question we would like to answer. So here's the schematic, right, of what we've described. So we have a generative model like Stable Diffusion, and we use this to generate synthetic training data in a targeted manner. Right? So we have 5% aircraft images, for example. And then we can train a classifier or some other sort of learner on top of the synthetic data. Okay. So in our case, we're going to fine-tune a clip model. All right. So based on the previous slides, we expect this to do well. Now, the idea we are going to study is that this generative model was itself trained on some real underlying data. Okay. So in this case, for example, Stable Diffusion 1.5 was trained on Lion 2B, right? So we know the training set. Okay. So what we'll do is we'll try to retrieve a targeted real subset of this data. For example, by searching Lion 2B for images where the captions mention an aircraft. Okay. And then we can training on targeted synthetic data with training on this upweighted targeted real data, so that we can deconfound these two factors and try to figure out how much are we getting out of targeting versus how much is the synthetic data giving us. Okay, so we'll get to your question by the end of this part. All right, so concretely, this is what the images look like. So given so here's an example from the test set. It's an Airbus A320, here's a picture. And so given these images, we retrieve real images from the data set, Lion 2B. And we also generate synthetic images based on the class label. Okay. And then we do this for all the class names, all the different data sets that we have. Okay. So at first glance, like they mostly look quite reasonable, although there are some artifacts like here that we'll discuss later. Okay. And I'm skipping some details that we'll just talk about in the paper, like how we apply data filtering and class balancing and so on. All right. Okay, so onto the result. So each column here is a different data set. And so the aircraft data set that we've been talking about is in the middle. And the top row is zero-shot accuracy using our CLIP model. Okay, and the bottom row is linear probing accuracy. And so zero-shot means we fine-tune the CLIP model and then we just use it directly. And linear probing is we use the labeled training sets for these different tasks. And we use that to train the linear layer on top of the CLIP model. Okay. Now the pink line is the off-the-shelf CLIP model performance. So before we do any fine-tuning. Okay. So you can sort of think of this as equivalent to training on untargeted real data. Okay? Because the CLIP model is trained on Lion 2B itself, right? Just from like a uniform sample of Lion 2B. Okay, so this is what happens. This is the baseline performance if you don't have any targeting. Okay. All right. So first takeaway is that synthetic data does help, at least on some tasks. Okay. So this is when we fine-tune synthetic data, and so consistent with the SynClear results in the linear probing setting, you see that the more synthetic data you have, then the better it does. Right? Although on many other tasks, it doesn't actually do that much. It sometimes even hurts performance. And in the zero-shot setting on aircraft, it also doesn't help. So we'll get back to this in a bit. Okay. So how does real data do? We find that the targeted real data outperforms or matches the synthetic data in basically every case we study. Right? And so this supports the hypothesis that the power of synthetic data here comes not so much from just the generated images being different, but it's because it allows you to target the training distribution. And this is especially useful for tasks like aircraft classification, where the task-specific data isn't very well represented in the general training corpus. Okay. All right, so why is there this gap between the real and synthetic data? So one issue is that the synthetic images are still not perfect yet. So they can be generally distorted, as you can see from this cat's face, or the propeller here is a bit sort of weirdly misshapen. Sometimes these distortions can actually change the class of the image. Okay, so this was supposed to be an Airbus A320, but it actually is only supposed to have one engine per wing, whereas Stable Diffusion generated a plane of two engines per wing. So actually the class name is now wrong, right? And we think this might explain why synthetic data only helped in the linear probing setting, but not the zero-shot setting. Okay, so in the zero-shot setting, the model is stuck with these noisy labels, whereas in the linear probing setting, it uses the representation it learns, but then it gets to use a clean labeled training set to fine-tune to train the linear probe. And so the synthetic data seems to be good for learning a general representation of planes, but maybe not so good for like saying this is exactly an Airbus A320.
So ask a question.
Yeah.
So the Stable Diffusion generated an image. I wonder it generated a real image, an image in another class in the real world, or generated something that does not exist in the real world. You mentioned because like Airbus is that type is supposed to have one engine per wing, but the generated image has two engines. So maybe this is something does not exist in the real world, or generate another type of airplane.
Yeah, that's a great question. I'm not sure. I don't know enough about aircraft.
I see.
If anyone knows if this is a real aircraft, let me know. But I would suspect probably not, just given what we know about the artifacts and image generation models, they tend to just create distorted versions as opposed to something else that exists. But yeah, good question. Okay, so sometimes the images can also be completely wrong, right? So these are supposed to be images of flutes, but they're not. Okay, a final issue is a bit more subtle. So even without these distortions, there can be distribution shifts between the real and synthetic data. And so for example, for these tabby cats, the real images, at least in this anecdote, have backgrounds that are cleaner and more of a solid color, whereas the synthetic images have backgrounds that tend to be more complex, more textures, more stuff happening. Right? And so it's not that this is worse than the other, right? They're all equally tabby cats, but there are these subtle shifts that are not captured in the captions. And in our paper, we have more details about how we analyze this, and we think that these shifts can play an equally large role as the previous distortions. Okay, so some takeaways from here. Right, so first is that the synthetic data does help on some tasks by giving us control of the training distribution. For example, by sampling more data from the target classes. Right? And we know this should work from Masashi's work and so on. And there's a lot of literature on distribution shifts and importance weighting. Okay, but if we can get a similar degree of targeting from the real data, then at least with current synthetic data, it still lags quite far behind the real data in the vision setting. Okay. Now that said, we're definitely not ruling out synthetic data. Like personally, I think it will be an increasing part of training ML models. And so I think the main message is just that it's still an open question. Like when do we expect it to work? Why do we expect it to work? And how can we design training algorithms that make the best use out of synthetic data? Okay. So for example, are there settings where it might be very hard to target by using retrieval because maybe the captions don't contain the exact class name, or you need a very specific combination, but perhaps with synthetic data it's much easier, right? So that's one aspect that we're currently trying to explore.
So behind the experiment, did you also consider standard data augmentation, like adding noise, rotation?
Oh, good question. I don't think so. Yeah.
If the classifier is the only issue, by adding those small noise or rotation, you can simply increase the number of data.
Right, yeah, that's true. So I expect that will do better for both the synthetic data and the real data. Yeah, and I think others have also. There's been a recent paper from Elisa at Berkeley where they use the synthetic model to do augmentations. Right, so they take like an animal and then they say use stable diffusion to edit the image, like change the background of this image. So it becomes like a generative model powered augmentation. Yeah, and that seems to do better as well. So maybe some sort of combination of real and synthetic data would work. Yeah. Okay, let me end this section by briefly mentioning two vignettes in which we do find that synthetic data helps. I don't have time to go through that in detail, but I'll just leave the links up. Okay, so first is a paper by Dao showing that synthetic data can be an easy way of making use of external models. So in this case, we use an external translation model to translate non-English image captions into English. Okay? And this increases the representation of concepts, right? So like the kiji, much more commonly described in Japanese captions because it's a national bird, I think, but less commonly encountered with English captions. Right? And this helps us train image text models that are better on both the more geographically diverse benchmarks, but also on some standard English language benchmarks like ImageNet. And so the synthetic data is basically a means for us to take in an externally trained translation model in this case. Second vignette is a paper by Jae-hoon on using synthetic data for text summarization. And here the idea is a common one. We can generate a lot of samples and pick the best samples with an external verifier. Okay. So for summarization, it's relatively easy to verify that the summary is correct compared to actually generating it. Right? Basically, given a summary, we can check that it's like below a certain length and that it has some amount of mutual information with the original text. And so we can generate a lot of samples, and we find that in some cases, 99% of the samples are not good summaries, but we just pick the best 1%, and that gives us a higher quality static training data set that we can then use to bootstrap the models. So using this approach, we bootstrap the 3 billion parameter Python model, which initially is just terrible at summarization, into a model that is competitive with ChatGPT at these paragraph level summarizations. Okay, cool. And please check out the paper links if you're interested in more details. Happy to take questions too. Okay, so that's the first part of the talk. Any questions, or I can go on?
I don't know if my question was answered though.
Mm.
Did you answer it? If you could.
So you mean like what happens if you upweight the? Yeah, so I think that was what we were trying to do with in this approach, right? Because the original data set is the pink dashed line, that's the untargeted real data. And we see that it does worse than the targeted synthetic data. Okay, so there are two things that are changing, right? The targeting and the synthesis. And so what we're trying to do is do the targeting, but on the real data. And
why don't you like change the coefficient when you train?
Change the weight.
Change the coefficient in front of the data set, like the objective. Just reweight them differently.
For different examples.
Yes.
We could try that. We haven't tried it, but it would still be different from this, right? Because upweighting a point is different from sampling more from that class. Okay, so especially in over-parameterized neural net settings, like upweighting does less because the loss is driven to near zero anyway on each of the training points. Whereas if you sample more points, then it actually changes the train model.
Yeah, I mean, they might be different. I just would like to see it.
Yeah, I agree that they might be different, but yeah, that's a good point. But I do want to emphasize that the synthetic data is not doing upweighting as well. So that would be a third variable. Like what happens if you upsample versus upweight? And in our case, we don't look at upweighting in any context. Yeah. Thanks for the question. Oh, okay. Let me move on to the second part. Okay, so changing gears a bit, right? We've talked about the joys of scaling up training data, such as through synthetic data. And now I want to switch gears to what happens if we instead scale up our inference time data. Okay, so this is work led by my student Roland. Okay, so some motivation first. Right, consider asking a language model a question like this. Right? Do current immunotherapeutics work well on solid tumors? Okay. We might hope to get a response like this, right? That where, for example, if it provides us with attribution so that we can actually go check if the response is correct, we can find out more details, or we can just assign credit appropriately. Okay, it's also up to date, right? Because the answer to this question changes, as with the years, and it comes from a credible source. Right? This is a peer-reviewed report of a clinical trial as opposed to maybe a forum post. Okay. Now the problem is that standard models are not great at any of these operations, right? Attribution, updating their knowledge, or prioritizing sources. Okay? And in my opinion, the root cause is that these models are fully parametric, in the sense that regardless of how large the training data is, it's once we're done with training the model, we don't need to keep around the training data anymore. Right? We try to ingest all of the information in the data into the parameters of our model, and then we just use the parameters to produce the output. So on one hand, so the operations that we want are all on the level of individual data points, like attribution and prioritizing sources. But on the other hand, the model works through the parameters. And I think this mismatch between the data and the parameters makes it challenging. So for example, attribution is hard because you have to go through billions of parameters to identify the training point, right, that was most influenced the model to generate some particular output. Okay? And there's been a lot of work on this problem, for example, through inference functions and other approaches, but it's still very challenging, and I think still an open problem. Okay. Now, updating knowledge is also hard because you have to get the new knowledge into the parameters and remove stuff from the parameters, right? And yeah, this is expensive. You might cause forgetting and interfere with other things that your model has learned. And even like prioritizing credible sources is also hard because we just don't even typically keep the source metadata in the parameters. Right? We just have chunk your training data and just feed it. Okay. So I think in my opinion, like this is why we should move towards developing models where the data points are first-class citizens at inference time. It doesn't rely completely on the parameters. So in our project, we do this via retrieval-based models. And so you're probably familiar with this, but retrieval-based models have access to a data store at inference time. And so this is also known as a RAG, retrieval augmented generation. And the data store contains a bunch of documents that are hopefully relevant to the query. So given a query, then we can then go and retrieve the most relevant documents from the data store. Right? So for example, we might fish out this paper, and then we can condition on the paper, on the retrieved documents to generate our output. And in the simplest case, which is the most popular right now, you just take the retrieved documents and you stick into the context, and then you run your language model through it. Okay, so this naturally supports, sorry, go on.
Is the data store from the training data, or it could be anything?
And it's a great question. I'll get to that in one slide. Oh, yeah, you guys have very good questions. Yeah, so keep that in mind. I think right now, typically the data store is separate from the training set. Okay, so this naturally supports attribution because you retrieve like a small number of documents, you know exactly which ones you condition on. Okay, it's also easier to update the knowledge because you're updating data points, so you're just adding or removing stuff from the data store. And we also have metadata on each document, right? So we can learn in the retriever to prioritize different sources according to the question we want to answer. Okay, and this is not as clean in reality because in reality, we still are using the parametric model, right? The parametric model might say whatever it wants to say without using the retrieve context, right? So there's still some ambiguity, but the more that we can make use of the retrieval step, then the easier it is to do all of these operations accurately. Okay, so retrieval models are not a new idea. Okay, so what's stopping us from using them just as the default model for everything? And so going back to MT's question, now one issue is that most academic work tends to use a small, highly curated data source, relatively small, on the order of a few billion tokens, such as Wikipedia. And this makes them more specialized and limits their applicability a bit. Okay. There's been some work on scaling these data stores up, but because of the resources needed, these have all been industry-led, and the data stores aren't open source. And in addition, some of these larger works, they have mainly focused on language modeling as opposed to some downstream tasks. I'll get to that in a bit. Okay, so our work tries to bridge this gap by introducing an open source trillion token scale data store. And in an attempt to answer this question, we've seen that scaling up our training data helps. Now, what happens if we also scale up the data store, which gives the model more access to data at inference time? Okay. So we constructed a web scale retrieval data store that's mainly based on Red Pajama. This is a open source web crawl. And we also added some more specialized data like scientific papers, math, code, and so on. Okay, and we design an efficient pipeline to do the scaling study on an academic budget. So let me talk a bit about that. Okay, so as a baseline, here's the naive pipeline. Okay, we start with the raw data. Okay, this is a naive pipeline. Like how do you actually build a data store? So we start with the raw data, and first we do data filtering. So for example, you might want to remove duplicates or remove short text and so on. And this is like sort of quality filtering. And then we subsample the data with some target probability P. Okay, and so why do we do this? So remember our goal is to sort of study scaling. Right? How does performance change with the size of the data store? So you want to subsample the data store to different sizes, and then measure the performance at each. So after we subsample, we have the data store of the right size, then we index it. So indexing means that we run through all of the data with a neural net, we get some embedding and we store this embedding for each of the points. Right? Okay. Now, given this index, we can then retrieve for each query, each test query, we can then retrieve the top K most relevant documents for the model.
Is the probability P coming from the test domain?
This probability P?
Yeah.
We just fix it to a grid because we just want to see the how performance changes with scale. Yeah, so it's just like 1%, 5%, 10%, and so on. Yeah. So test domain independent. Yeah. Okay, so then once we evaluate, so the test query here is coming from the test set. Right? So we take a test question and we retrieve the top K documents that are relevant to that question, and then we evaluate it. Okay, so far so good. Okay, now the problem is that each different choice of the size, which is the probability P, or the composition of the data store, or the kinds of filtering we do, right? Every time we change, or the random seed for variance, every time we change that, then we need to rebuild the index, which is computationally expensive. Okay, so the trick we use is a simple one. We basically just reordered things so that the more expensive operations come first and you are less likely to have to redo them. Okay, so we start by indexing the full data set, like the trillion token plus data set. And then we jump straight to retrieving the top big K documents for all of the test queries. Okay. And then after that, we only do the filtering on the retrieved documents. And likewise, we only subsample the retrieved documents, okay, instead of the raw data. So you basically take all the pre-processing steps and do it only on the retrieved documents as opposed to the raw data. And the trick is that is to pick big K large enough so that even after filtering and subsampling, you end up with at least small K documents that you can use for evaluation. Okay. So in practice, for example, small K is like 3. So we take the top 3 documents from each query and use it to answer the query. And big K is like 1,000. Right? So we retrieve 1,000 documents and then we can subsample it, down to 1% even. And with standard concentration arguments, with high probability, you have enough documents left over after sampling so that you can still do the evaluation. Okay, let me pause here for a bit. Okay, sorry, and with this, so whenever we want to change, for example, P, which is the size of the data set, we just need to redo this last subsampling step. And we don't have to rebuild the index or reconstruct everything. Okay, any questions?
Is it good for doing experiments or is
Yeah.
it for real applications?
Great question. Yes. So this is terrible for real applications. It's only good for doing experiments. Yeah. Or rather, like this is what we do because we need to run this many times with different settings, right? In order to find the right configuration, right? Or to see how the performance changes. In a real application, you have one data store and you just build it once and then you're good. Okay, so this has no bearing on what you actually do if you're running it. It's more about how do we efficiently study all these different choices in the data set. Yeah, great point. Okay, cool. Okay, so on to the result. So on the x-axis is the size of the data store in tokens. On the y-axis here, we are plotting perplexity, which is a measure of language modeling performance. The lower is better. Okay, and these are 2 different data sets. Red Pajama on the left is, as we mentioned, a web crawl, and Stalk on the right is a collection of scientific papers. So just 2 different test domains. Okay? So we find that the performance improves, the perplexity drops as we scale up the data store. This is true on both Red Pajama and Stalk, as well as on the 3 different llama models we show here. Okay, so the dashed lines are the model performance without retrieval. Right? So with no data store. And you can see that smaller models, like the yellow line is the 7B model, can outperform larger models like the red 13D model once you have a large enough data store. The same story holds for downstream tasks as well. Okay, so here we plot trivial QA and natural questions. These are both the factual, sort of short answer question, QA questions. And so as with perplexity, we find that smaller models with a large data store can do really well, and they're better than larger models without one. Okay. On MMLU, which is the widely used multiple choice reasoning task, the improvement is less dramatic. You don't get that lines crossing, but there's still steady improvement. And unfortunately, it's less effective for MedQA. So MedQA is questions from medical licensing exams that generally require more reasoning. And retrieval doesn't do that well here. So I think there's still a bunch of work to be done on improving reasoning-based tasks with retrieval.
Have you done the, like, you put the data store in the training data and then you get a model? That should be an obvious baseline, right?
You put the data store in the training data. Yes. So the models are trained, the data stores here are more or less subsets of the training data. It's hard to tell because Llama 2 doesn't release its training data, but it's all based on web crawls. Yeah.
It's not clear to me if the data store, should be if it's a different thing, then it's all changed, right? Because it's you could have just put it as a training data.
That's right. So I think there's a great question of, is this coming from because our data store is special somehow, right? Or is it from retrieval? We don't think our data store is that special compared to the training data because these Red Pajama is sort of a worse version of the Llama 2 training data.
So then the reason for improvement is?
The reason for improvement is that it has access, it can retrieve the right things and then use them directly. And so I guess it's hard for these models, especially the smaller models, to store all the information in their parameters, even if they have technically seen it before once in the training set. Whereas if you can pull it out and put it in the context, then it's able to answer better.
So can we say that somehow it's replacing the parameters of the larger model data?
Yeah, exactly. So it's sort of a non-parametric approach, right? Where your capacity of the model scales with the data store size as well as the parameters. Whereas for a fully parametric model, the more training data you have, like you still have finite capacity. Yeah, that's right. There is still one, so very related to your question. Is one point is that indexing this data store takes time, right? So you still have to make a full pass through the trillion tokens. So it's not quite fair to compare it just to the pre-trained models, which you could have used the same amount of compute to just train a model more. Okay, so we try to account for this in the following way. We plot the model performance against the total amount of training compute. And so this is the pre-training flops plus the flops needed to construct data stores. Okay. So on this sketch, right, we have models of different sizes. So you can see here, sorry, it's a bit light. And for each of these different sizes, we also have different amounts of pre-training data. Okay, so you can train a larger model for longer. Right? So the larger the model or the more data you train it on, the more compute it takes. Okay, so we can plot all of this and then draw the Pareto optimal front. Okay, so this is like for the best for a fixed amount of compute. Here's the best performance you can achieve. Okay, and then now we can add retrieval to this plot. So for each of these model checkpoints, we can add a data store. Right? And so when we add a data store, it takes up more compute, but also changes the performance. Okay, and it gives us a second Pareto optimal curve for retrieval-based models. And you see that generally, on the low end of this, adding a data store does take quite a bit of compute compared to pre-training. Right? But on the far end, adding the data store barely changes the amount of compute. And that's because typically the data store is constructed with a much smaller model. So the model used to embed the data store is smaller than the larger elements. Okay, so now we can compare these two Pareto curves, right? So here are the actual results. So we use the OMO model family from AI2 because they release all the checkpoints. And so we have different checkpoints for different amounts of training and different model sizes. Okay? So we can see that for the same amount of compute, the red line, the retrieval models do better. And we did the same study with the PyTear models, which also released all their checkpoints. And we see similar results with the exception that on MMLU and MetQA, the performance of these models is older generation models. The performance is so bad that it's like kind of random chance and retrieval doesn't help. Okay. Now one thing I want to note is that this is just training time compute. Okay. So test time compute is a different story. At inference time, retrieval models take longer at inference time because first you need to do the retrieval, which typically can be done on CPU. But then you take the retrieved documents and you put it in the context, and then you have a longer context time that you need to process. Right? So it's slower at inference time. But that's it. On some of these tasks, at least for trivial QA and natural questions, you can get away with using a much smaller model and have better performance with retrieval. So the total amount of time you need might still be less at inference time because you use a smaller model instead of a larger model. So exactly which one is faster really depends on your application at inference time. But for training time, the story is much clearer that it doesn't take as much time to train. Okay.
So can you explain more about how you index the documents, the stuff? You only use deep learning based, like a large language model based methods.
That's right. Yeah. So there are a variety of ways to construct the index. We just took a popular off-the-shelf one called Contriver. There are deep learning based ones which are so-called dense retrievers, and then there are some more classical approaches which are called sparse retrievers. So sparse retrievers do things like BM25. They try to find the keyword matching.
So you have already combined the traditional information retrieval and the
yeah, we tried out a bunch, but the dense ones work better than the sparse ones, at least in our case. And the dense retrieval methods essentially you construct a feature representation for each of your documents. And then when you have a test query that comes in, you also have a construct feature representation for it. And then you do a fast approximate inner product search to find the retrieved documents with the largest inner product. And that's how you do retrieval.
Yeah, because to me, if the problem is somehow more difficult to learn, maybe the sparse retrieval can sometimes not better than, but can offer some complementary information.
Yeah, completely agree. Yeah, so if you have a new word they've never seen before, right? Your neural model might not know how to represent
or sometimes that. Because it's a very rare word, but it's a term. So we really want to have some exact match.
Yeah.
But if you use dense, the deep learning based retrieval method, you will only care about the semantic meaning of the word.
Completely agree.
Yeah, sometimes maybe the meaning is the same, but some word is really kept as a term in some research area. Sometimes.
Yeah, I completely agree. So I think there's a lot of open problems in just how to build better retrievers. People try a combination of sparse and dense. I think we tried that actually, but the sparse retrievers are much slower. At least there aren't fast open source implementations that we could use.
I see.
And so we sort of struggled with doing this at the trillion token scale, just in terms of compute. Yeah, great question though. Okay, let me wrap up this section with one last set of results. So we also studied what happens if we use a specialized single domain data source like in prior work, right? Instead of our big data store that just combines everything together. So here each row is a task, the same task we've been looking at, the 4 downstream tasks and the 2 language modeling tasks. Each column is a separate domain, right? And so for example, PubMed data, math data, scientific papers, books, and the last column is our data store that combines everything together. So each of the middle columns is a subset of the last column. Okay. So we found that the multi-domain data store basically outperforms or matches all of the in-domain data stores. And I think this is quite interesting because when we look at parametric models, right, and based on the first part of the talk where we talked about this targeting and distribution shifts, and we typically worry about distribution shifts and data composition and competition between domains. Okay, so for example, if you train a model on more PubMed data, you might expect that it gets better at medical stuff, but probably gets worse at coding. Right? And one reason is because we have fixed model capacity, right? Going back to our discussion earlier. So if you allocate more of it towards medical stuff, you probably allocate less towards coding. And so in practice, this means you have to be very careful about weighting the different domains that you sample from in your training data. Right? There's a whole art to that. But in our case, the model capacity grows with the data store size. So it seems like we don't really have this issue as much. And one potential reason is also that the retriever is helping to manage this domain weighting. Okay, so in our data store, right, most of the documents are from Common Crawl, so it's web crawl. And maybe we have about 5% from scientific papers. Okay, but if you look at the distribution of retrieved documents for the medical QA task, you see that the sort of scientific papers from PubMed and Pesto have been upweighted by more than 10x. Whereas if you look at the retrieved documents for natural questions, which is just generic common sense-ish questions, then you see that the wiki pages have been upweighted by like 70x, right? Because many of these questions can be answered by doing a Wikipedia lookup. And so because the retriever is somewhat capable of figuring out what's the relevant domain to retrieve from, it doesn't really hurt us to just put everything into the big data store and let it figure out the right domain to use instead of having to do the domain weighting a priori very carefully. And so we can hope to build larger, more general purpose data stores this way. Okay, great. So let me conclude. So scaling up these data stores improves performance on language modeling and downstream tasks. And so we think that we should consider the amount of inference time data as a new dimension of scaling, in addition to the amount of training data and the amount of parameters, which are what we typically consider. Now, going back to the motivation at the start of this section, right? So more zooming out a bit, we are excited about models that can reason directly over data, right? Because I think they help us to do things like attribution and prioritizing sources and so on. And there's a lot more work that we would like to do on actually directly supporting these operations that we talked about, attribution, updating knowledge, as well as improving reasoning, as you saw from some of the performance plots. Okay, so all of our work here is released open source, so please check it out if you're interested. Okay, great. How much time do I have left, just to check?
You can continue.
Well, okay.
Can I ask a question?
Yes.
So we're coming back to MP's original question. So suppose we have many test domains and already we have some data from the test domain. So why don't you take all the data back in the training, retrain the entire system?
Sorry, could you repeat it?
You have a number of test domains and
yeah.
you collect test data.
Yeah.
Then so put all the data back in the training data set, retrain the entire system. Of course, doing this for each test domain is not a good idea. But at some point, okay, you have large number of test domains and you have big data already from the test domain.
Yeah. No, I think that
it's like an iterative process.
Yeah, exactly. And I'm sure that will improve performance. But just to clarify, our data stores are not targeted to the test domain either. So we just take a general purpose data store and we use that, and then so it's sort of, we are not doing any further specialization of the data store.
So in a bit longer run, of course, fine tuning or test time adaptation, these are quite useful in reality. But if we do this for a few months, then already we have enough number of data.
Yeah.
I think that's happening like every 1 year, or every 2 years. Like from GPT-2 in 2018 to GPT-3 in 2020. But if It's like the stable delusion, a stable version or the development
Yeah.
version of the software. Which version you want to use?
Until we have the next version,
Yeah.
we could try this kind of adaptations.
Yeah, no, I completely agree. And even with stable, even with like the next run of next generation models, people will fine tune them towards medicine, towards coding, towards math, and it will do a bit better. But I do think that overall, even if the parametric model gets better, and we do need to improve this, right, I think that having a model architecture that can reason about data points, so as a first-class citizen, I think that is still helpful. Right? So we can and should fine-tune our models to make them better suited for the domain. But when we want to do things like attribution and updating knowledge and so on, it's still, I think, easier to do that with some data store as opposed to only going through the parameters. So I think we want both.
Maybe there's value in storing data. We haven't thought of this. Always putting everything in the parameter. I mean, of course, there's always reason that attribution is important. But we don't know that actually have storing training data, for example. It actually improves things at inference time.
Yeah, exactly.
I have a question.
Yeah.
How to update the data store? Maybe because the data is continuous coming, so how to select which data to store? Maybe.
Yeah, great question. There has been work on actually Graham has a paper on this recently. But I think so. For example, for scientific papers, right, you can just update your index. Right, every day you take the latest papers and you put them into the.
But this data store is become larger and larger. We cannot store all the data, and we must group some. But we need to drop certain percentage of the papers. Yeah.
Right. So I agree. So that's a good question. And I think there's still a lot of like supporting each of these operations. I actually think it's an open question. And like, how do you actually do attribution? Because, for example, you might retrieve 10 documents, plus some of it might come from the parameters itself as opposed to the documents. How do you actually attribute? It's easier, but it's still an open problem. Updating is also if you have constraints on your data store size, or maybe you want to kick out old information that's obsolete, but keep the new one, that's also an open problem. Yeah. Okay, great. Let me wrap up the last part. Okay, so for the third part, I want to talk a little bit about evaluation now. Right, so in particular under interactive clinical settings, this is work led by Stella. All of this work is done by my first year students at UW in the last few months. So, okay, so the setup here, right, as you mentioned earlier, is that most of this data we've been talking about, it comes from static sources like these. And so even when the data is scraped from sites like Reddit that are supposed to be interactive, right, we tend to lose the interactive aspect once it gets converted to training data. Because we just chunk the data into short chunks, we don't keep the context around and so on. Okay, so it removes this sort of conversational interaction. Now, at the same time, models are also mostly evaluated in static settings. Okay, so for example, in medicine, we talked about MedQA and benchmark, which is based on exams, official exams, right? And in those benchmarks, right, the model is given the question and then it produces the answer, but there's no back and forth. These benchmarks are the basis of claims like this, right? Where models like GPT-4 have reached clinician level performance, such as in this paper. And to be clear, these benchmarks are very helpful, right? We use them in the previous section, right? But they're still incomplete because many real-world applications require models to interact with users. So for example, in a primary care setting, so it's very unlikely that as a patient, you go to the doctor and just say all of this at once, right? It's more likely that maybe you come in and say, I have a fever, what should I do? Okay? And then the model will need to interact with the user in order to elicit the right information. So our goal is to evaluate models in such settings. Okay, so that's so fun. How do you think current state of the art language models do? Okay, if you ask GPT this question, okay, I have a fever, and what is happening? So GPT told us to drink more water and rest and talk to a healthcare professional if needed, okay? Which is very sensible advice. It's probably right for most people, but it's not quite what we would want from models, especially if you deploy them in a healthcare setting. Okay. So a more realistic interaction might be something like this, where perhaps the model asks, okay, what is your temperature? And the patient responds, sorry, these are the wrong units. This is a high fever. And so the model might ask, okay, have you traveled anywhere recently? Blah, 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 and so on and so forth, until it's more confident about giving an answer. Okay, so we can abstract these kinds of interaction into the following evaluation framework, right, where we start with a question like, I have a fever, what should I do? And we have an expert system, there's an AI model that we're trying to evaluate. And the model gets to decide, does it have enough information to answer or not? And if it doesn't, then it can ask a follow-up information seeking question. Okay? And that question goes to a different AI system, which is the patient. Okay? And this patient system has privileged access to the patient information. So you can use that to respond to these questions. Then the expert gets to see this response and it iterates again. Okay, now do I have enough information? And if yes, then it gives the final answer that we can then evaluate against the benchmark answer. Okay, cool. So we have these standard benchmarks, right? And they contain examples like this, right? So there's some context here in green, which is the full information on the patient. And then there's a question and the options in purple. Okay? So here it's like, a question, which of the following is the most likely cause of anemia? And then the context is like all the information on the patient. Okay, so you want to convert this into our interactive framework, right? So, okay, so let's start with some baselines first. So this is the standard setting where we give all of this information to the model at the start. Okay, so this is the same MedQA task that we saw in the second section. So this is a non-interactive full information setting. And as you can see, the new models like GPT-4 do quite well. Right? They're actually comparable or better than the average human doctor on this task. Okay. The second baseline is a non-interactive but limited information setting, where we just give the initial information, which is the first sentence of the context, and we don't give any of this. Okay. So most of the time, the question is not actually answerable because you only have one sentence. So you can see performance drops quite a bit, although it's still well above random chance, which is 25%. So you can sort of guess at a lot of these questions. Okay. Okay, so now the interactive setting, right? This is, we'll follow our framework where the expert system only sees the limited info, but the patient system gets to see all of the context from which it can answer questions. Okay. And so the expert can ask questions of the patient information, the patient system. And it can ask like 20 questions, so more than enough to get all the info if it asks the right questions. And then it will decide when it has enough information and outputs a final answer. Okay. Okay, so how well do you think this will do? Right, so it starts with the limited info, but it can ask questions to get you to the full info. Right? Okay, how much of the gap do you think it will close? Just curious. Who thinks it will close more than half of the gap? Or less than half? Anyone else? Okay. So actually it drops the performance compared to, for everything except GPT-4. And it's even worse than limited information, which is surprising because it has strictly at least as much information, right? So we looked into it, and the issue is that first, the LMs don't ask a lot of questions in the first place. And when they do ask the questions, the conversation format, which is interleaved, confuses the LM, which drops the performance. The newer models like GPT-4 are more robust to that, so it remains about the same. Right? So this is just with a basic prompt that asks the LM, are you confident or do you need more information? So we tried our best to prompt engineer it. by encouraging it to ask questions and doing self-consistency and chain of thought and so on. And in this case, it does close more than half of the gap. But there's still nevertheless a big remaining gap, right, between the non-interactive full setting and the best interactive setting. And so for example, for MedQA, you go from 54 to 66, but then there's still like half of the gap left to 79. Okay, so a lot more work to be done here. It's still not yet near human expert performance under more realistic settings. Okay, so on the data end, there's a lot we can do to collect or synthesize this kind of multi-turn data. But beyond the data, I think there's also, so we need to adapt our methods to the dynamic settings. So let me just give you a quick preview of one example you're currently working on, which is about conformal inference. So conformal inference, as you might know, is an approach to generating prediction sets as opposed to point predictions. Okay, so instead of a single label, you say, here are some possible labels. Okay, and it has the property that there's some guaranteed statistical coverage that on expectation under exchangeability ID settings, the true label is going to be in the prediction set some percentage of the time. So of course, you can always say my prediction set is all possible answers, and then we get 100% coverage, but also be useless. So generally, we set a target coverage, let's say 90%, and then we'll run conformal inference to produce the smallest possible, hopefully the smallest possible prediction sets that achieves this coverage level. Okay. Okay, so this is relevant for our purposes because we can use this for the interactive setting, right? Like if the prediction set size is more than 1, then we are still unsure, so we can ask a follow-up question. But if it's exactly 1, then we're like, let me just output this prediction. Okay. Now the challenge here is that the size of these prediction sets affects the data that the model sees. Right? So we have this sort of non-stationary problem where if you have larger prediction sets, so you're less confident, then you ask more follow-up questions. So then the model will see like longer chains of conversation. Whereas in the standard conformal setting, you assume that the data points are completely fixed and given to you, independent of your conformal threshold. Okay, so standard inference techniques, conformal inference techniques don't handle this well. So let me just illustrate this with a plot. On the x-axis, we have the target coverage, which is a hyperparameter input to the algorithm. And on the y-axis, you have the empirical coverage of the prediction set at test time. Okay, so ideally, we want to get points on this line. Okay. So if you set your target coverage to 80%, you should get a 80% empirical coverage. This is in the IID setting. Okay, but with standard conformal inference techniques, we actually get significant under coverage. This is on MedQA. Okay, so if you set a target coverage of 80%, you actually just get 60% empirical coverage because of the non-stationarity. And this gives a false sense of security. And so we are trying to work on an adaptive conformal method to remedy this gap. That's currently in progress. Hopefully it'll be out in the next couple of months. Okay, so let me wrap up the section. Right, many real applications are
I have a small question.
Yes.
So in the data sets we have considered in this part
Yeah.
3, so there is only a single correct answer. Is this realistic for medical domain? It's like the correct answer is deterministic.
I think it's I think it's to first order. I think it is realistic. So, for you imagine you're a patient with suffering from some illness. There is a correct answer of what illness it is. Right? The patient might come and just describe 1 or 2 symptoms, and the doctor might want to order more tests or ask questions. But at the end of the day, so biologically, there's one ground truth illness. Does that make sense?
Okay.
That you're trying to uncover.
Yeah, but it's quite a different experience when we go to see the doctors. Because in many cases, they cannot tell us why we are sick. And
Okay, that's true, but there is a difference between the doctor cannot tell and the reality there is
the doctor cannot identify the reason. Okay.
Yeah, but also in our settings, right? These are exam questions, so there is a right answer, and the information needed to get to the answer is in the question, is available.
Yeah.
Because they were set in such a way that they can be answered
I
by humans.
understand that maybe because they are exam questions, so they are simplified
Yeah,
compared with the daily practice of doctors.
yeah, exactly. So this is still not like fully realistic in the sense
Okay.
of that. Yeah, for sure. Okay, great. So yeah, our current benchmarks don't reflect a lot of this difficulty of interaction. So I think there's a lot of future work here that will be fun. There is a recent paper from Google that tackles a very similar setting. You're also using a lot of synthetic data to train their models on this. So I think that is one promising direction for generating this sort of multi-turn data. Okay, our benchmark is available online, so feel free to check it out if you're interested. And that's it. So these are the questions we covered, and I'd like to thank my students and collaborators for doing it. Happy to take questions. Great, thank you.
I have a question about the last one.
Yeah.
So you have the patient model that can access full information. And I don't know, is a privacy problem here? Because once the patient system reply to the expert system, then all the personal information is leaked to the expert system.
Yeah. No, that's a great question. So in this case, we are using this just for evaluation. Right? So the standard setting, you will give all of the information to the doctor, and now it's just all the information in the patient system, but the doctor only sees a subset of the information. So I guess these exam questions are written such that there's no private information in the question. And in a real clinical setting, you assume that the patient would also be happy to volunteer the answers to the questions the doctor asks, I guess. Yeah.
So still, it is much better than giving all the information to the doctor.
In terms of privacy, yeah. But I mean, in this case, we are not considering privacy in the sense that we want the doctor to be able to know all the information about the patient by asking the right questions.
Once the patient really allowed the doctor to access all the information, maybe I want to go back to the second topic, and the retrieval approach to have a better answer from the expert system.
Yeah, that's right. Yeah. And so actually the patient response also, so the way we constructed the patient system, because if we just use free-form responses from the LM, the patient system might hallucinate stuff about the patient. So the patient response is limited to picking sort of spans from the patient info. So it returns the real info there. So it's sort of like retrieving the right parts of the patient info. Yeah, good question.
Yes, any questions here? There are two questions from the online chat group, but I think maybe we can first answer questions offline, and then we'll turn to the online chat group. Is there any questions?
Also, in the last experiment, is the patient human or rule-based system?
Oh, so the patient is a language model.
A patient is a language model.
That's right. Yeah.
How about the expert?
Yeah. So expert is the language model that we want to evaluate.
Oh,
right. So this is the evaluation benchmark.
Oh, patients have more information about the
That's right. Yeah. So the patient gets to see the full info, and then it answers the question knowing the full info.
Oh, okay. So I'm wondering, how to generate effective questions to ask the patients.
Yeah, that's exactly what we're trying to evaluate these models on, right? So this is the high level goal is that, okay, if you look at standard benchmarks, it doesn't evaluate the model's ability to ask questions, right? It assumes you get all this information and just evaluates your ability to reason from the information. But what we're trying to say is that in reality, you need to know how to ask the right questions, and therefore this is what this benchmark is evaluating. Now, how do you actually do that is a separate question. Not sure. I think there's a bunch of approaches people are trying. So one is through synthetic data. Another is through doing trying to take some classical approaches for planning. So for example, like 20 questions. If are you familiar with the game where you have to I say I'm thinking of an object and you have 20 questions and yes, no question, right? So then each question you want to try to like cut the search space in half and stuff like that. So people are trying methods like this too.
Also, maybe I think if you use two language models to complete this, maybe the expert system could ask some questions hard to answer. For example, may I ask, what yield do you get?
Yeah. So the expert could just be like, hey, what's the answer to this question or something, right? So that's what I was saying. The patient system, we constrain it to only return like specific facts that are already in the patient info. So specifically, we first pre-process the patient information, which comes in a paragraph, right? So it comes like this. And then we break it down into atomic facts, like the patient is 27 years old, the patient is G1P0, the patient is 9 weeks gestational age, and so on. So we break it down into a list of facts, and then the patient model is constrained to just return facts.
Okay, so what is the effect of the constraint?
Yeah, so in our paper, we have a study of like, how accurate is this? And we find that this is better than just letting the LM respond free form, because the LM, if the patient LM can respond free form, it might just make up stuff, or it might give the answer away, or the expert might say, tell me all the relevant information, and the patient just gives everything. So we want to be able to control for that.
Okay.
Yeah.
Okay, there are also two questions for the online chapter.
Yeah.
First, I'm also interested in how doctor thinks. What is their version of clinical pipeline? That's the first question.
What is their version of the clinical pipeline?
Yeah.
So I think I'm not a real doctor, but I think it is definitely more realistic that we've talked to some clinicians as part of this project, and it's more realistic that you start with imperfect information, right? And you need to figure out what is the right thing to ask or what's the right thing to test. Compared to the standard benchmarks are very unrealistic in the sense that you rarely get all of the information that you need handed to you. And these exams are not just that you have all the information handed to you, but by construction that these are the only information that you need because someone set the exam so that you can answer it. And that's an unrealistic expectation.
Okay. Then the second question is, could you share the GitHub coding response for the conformal prediction? That's for the
we will do that once it's out. It's not yet out, but hopefully soon.
Oh.
Yeah, thank you. The preprint is not out yet, but we are writing it now.
Okay. So, is there any other questions?
Okay, right on time then.
Yes.
Cool. Okay, thank you everyone. Thank you those on Zoom.